Alright, so first off, I need to apologize to my second period if this video comes too late. got home pretty late today and just managed to whip up this video. And this video is going to cover in the 2D kinematics, the gist of what you need to know for this upcoming quiz, which is pretty much going to be problem solving for both a horizontal projectile and an angled projectile. Okay, so the first idea I'm going to talk about is the independence of motion in 2 dimensions. And so when you have objects moving in 2 dimensions or even 3 dimensions, they have motion with both horizontal and vertical components, but if you're in the 3rd dimension, then it's going to be that z-axis. So horizontal refers to x, vertical refers to y. And these components act independently of each other, but simultaneously as well. So x and y, they don't affect each other. And in terms of being happening simultaneously, time is the only linking variable. So they have 2 perpendicular components. They don't affect each other, but they act at the same time. And so the first projectile motion scenario we're going to look at is the horizontal projectile. And this is when you have an object being launched horizontally at first. And so it's going to have a sort of parabolic path that starts out horizontal and then it starts to curve in the downward direction, like you can see here. And so it's set up at a certain height above the ground, it covers a certain horizontal distance, and it's being launched horizontally. Now, what else does this mean? So while we have an initial horizontal velocity, this also means that the vertical velocity starts from 0. And so you'll start to see that the arrows, the vector arrows for the vertical velocity start to increase and grow with length over time as the object accelerates downward, like you can see here. At the same time, the horizontal component stays the same. And that's because we have no horizontal acceleration. It's 0 meters per second squared, and that's because we ignore air resistance. Now, the reason why it starts to accelerate vertically is because gravity is the only thing acting on this object. And so it accelerates with 9.81 meters per second squared. Alright, next I'm going to use some homework problems as an example. So if you have that 2D kinematics homework, you could just take a look at number 7 to show an example of a horizontal projectile. So here we have a penny kicked horizontally off the roof of a 10-story building 33.3 meters high. It is kicked at a speed of 22 meters per second. Alright, so here I showed the diagram, and you pick out your values, separate them into x and y in the T-chart format. You don't have to do this, but I do find it useful for problem solving because I see the tendency for you guys to get your variables mixed up. There's a lot you have to pick out, so I highly suggest you separate it and organize it in this T-chart format. You don't have to, once again. Okay, so I'm going to work out these problems in the meantime. Part A, they're asking for the initial horizontal velocity, and that's the initial velocity stated in the problem, 22 meters per second. Part B is what is the penny's initial vertical velocity, and that's 0 meters per second. Notice it's only starting out horizontally, so it doesn't have anything to start with vertically, so it starts from 0. Now part C, how long is the penny in the air? So we're looking for time. And we could solve for time looking at our variables in the y direction. We don't have enough pieces in the x direction, so we're going to focus on the y. And if you look at those big 3 kinematic equations, we could use the middle one, d equals vit plus 1/2 at squared. Please remember you're sticking to just the y variables. Oh, look at that, it just disappeared. Okay, so plug it in, just the y values. Get t is going to equal to 2.61 seconds for its air time. Part D, how far away from the building did the penny land? So this is a horizontal distance, how far? And the good thing about this is that you can drag that t value, that time, into the x direction. They're going to happen simultaneously, so you could solve for dx. You get that dx is equal to 57.42 meters. Alright, and part E is how fast vertically, keyword vertically, is the ball traveling when it hits the ground. So this is right before it hits the ground. It's not going to be 0, even though once it hits the ground it goes to 0 meters per second, but we're looking for when it, just before it hits the ground. So it's going to be an actual number here. And so you can use VFY equals VI plus AT, plug it in, and you solve for VF to be 25.6 meters per second. Okay, now we're going to go on to angled projectiles. And look here, we have our diagram. Alright, much like the other scenario, the X motion remains constant while the Y motion replicates an object being thrown upward and accelerating back down once it reaches the peak. So it starts to decelerate until the peak is reached, and then acceleration happens on the way back down. The velocity at the peak is 0 meters per second vertically only. And then initial velocity, if you notice, is broken up into its X and Y components. This is the first thing you must do. It's often symmetrical. Complementary angles share the same range value, dx. And then if you look at the top right corner, you'll see the critical angles needed for certain values. If you want to maximize your horizontal velocity, 0 degrees, 45 degrees maximizes that horizontal distance, and 90 degrees maximizes both the air time and the vertical components of velocity and distance. Alright, so looking at the last problem to show angled projectile, and this is homework problem number 10 with Tom and Jerry. So let's say Tom hits Jerry with a racket at a 75-degree angle with a speed of 60 meters per second. Here we're going to start solving for the components of the initial velocity, 60 meters per second, at a 75-degree angle. And here, using sine and cosine for x and sine for y, you should get 15.53 meters per second on x and 57.96 meters per second for y. And then you fill in your values on the t-chart before we begin. So A is asking for the total time in the air. Please note, we can only solve for the time going up towards the peak. That's only half the journey. Once you plug and chug, you should get a time of 5.91 seconds to the peak. You double that to get the full arc. 11.82 seconds. Alright, part B, this time asking for how high, so that's a vertical distance dy. So we're focusing on just our vertical components. And once you plug and chug, you can use the half time, because that's the time it takes to go from bottom to top to the peak. Don't use the total time, just make sure you don't do that. And you should get that dy is equal to 171.22 meters. And lastly, part C, we're looking for how far across. That's a dx, horizontal distance. Use our trusty equation, V is equal to d over t. Plug it in, 15.53 meters per second times our total time, 11.82 seconds, and you should get 183.56 meters. Notice that number 11 follows the same scenario, just 15 degrees. Hint, hint, they're complementary angles, so they should share one similar value between them. That's up to you guys to figure out.